Okay, hello everyone. So today's lecture is on temperature sensors, and we are going to use Arduino. Um, and we're going to learn that how we're going to, some basic circuitry required, um, which we can use uh, with temperature sensors and acquired that information digitally using Arduino, because this microcontroller, as we know, it's very easy to use, easy to program, and easy to learn, and that is the reason behind using Arduino as a microcontroller with temperature sensor. But the main purpose or the main um, focus of this lecture is to learn about temperature sensors, different type of temperature sensors, and their main properties, features, capabilities, and using it with microcontrollers or microprocessors for the respective purposes, or with the respective customer, client, internal or external needs. Okay, so let's keep going with today's lecture. As I mentioned before in almost every lecture, that if there is a word which you feel not comfortable with the meanings, I highly recommend to see the respective dictionaries like Oxford, or simply just googling it, their meanings, and you will find the meaning of that particular word. And that is a very, in my opinion, is a very good practice for you to be more knowledgeable, well informed, because the words are selected for a certain reason, and the word themselves have lot of meanings inherent in them to understand that particular concept. Okay, so let's carry on. So there are three type of temperature sensors, and one is RTD. RTD is very easy, for R for resistance, T for temperature, and D for detectors. So these type of sensors have their resistance varying with temperatures, and that's how we detect the temperatures. And we will learn how we do that. The second time is thermistors. Thermistor is a combination of two words, a term for temperature, resistor. The ISTOR S is the word from resistor. So combining these two, temperature and the word resistor, is the term thermistor. And we will learn how they differ with RTD. Or the third type is thermocouples, and we will learn all these three different type of temperature sensors, their features, capabilities, pros and cons. The most important point here, in relation to using temperature sensors, but not only temperature sensors, any type of a sensor, or in my based on my experience, in any system design, calibration is a very important term you need to understand. That, like for example, you're going to use any type of a temperature sensor, and that requires what we call it as, in this particular lecture, we will call it as sensor calibration. So we have to calibrate the sensor in order to read accurate values from that particular sensor. But as I just mentioned, that word calibration applies to any system design. Any system means analog, digital, or mixed signal system you're designing. You need to calibrate that system, okay, in order to measure the parameter with a highest degree of accuracy in order to achieve your design objectives. Okay, but anyhow, so the important thing for you to here to learn is there are three type of temperature sensors: RTD, thermistors, thermocouples, and they do require calibration. And added on top of that, as I mentioned, calibration is a feature which goes along with most of the system design. Okay, so let's carry on. So what is the learning objective of this engagement? The lecture is to get the differences between, to know the differences between different type of sensors and their calibration schemes, using Arduino as a microcontroller to read digitized values of temperatures for respective plant actions. And in our case, what we are going to do, we are going to use Arduino and to simply turn on an output LED indicating that the temperature has surpassed or crossed the set threshold point. And so I think in this way it will be, we will use a simple kind of a circuitry in order to achieve our learning objectives. Okay, so let's move on. So as I mentioned you before, RTD stands for resistance temperature detectors. The three main categories of RTD sensors are thin film, as you can see this is thin film, wire wound, this is wire wound, and coiled elements. So coiled element, there are three types of RTD sensors. While these types are the ones most widely used in industry, other more exotic shapes are used. For example, carbon resistors are used at ultra low temperatures, minus 273 degrees Celsius to minus 173 degrees Celsius. And here are some of the very important bullet points. Before we discuss the bullet points, since I already discussed this thin film, wire wound, and coil elements, and the term next to it is PRT, and PRT stands for platinum resistance thermometer. So platinum is a material, and so sorry for that, it's just PRT, as I said, platinum resistance thermometers. So platinum is a material, and R for resistance thermometer. So we are using PRTs in these three type of RTD sensors. So many RTDs consist of a length of a fine wire wrapped around a heat resistant ceramic or glass core. So as you can see here, the wire is wound, across a ceramic or a glass core. RTD wire is a pure material, typically platinum, but it can be nickel or copper. Materials used have an accurate resistance temperature relationship, which essentially is accurately estimating temperature, and we will learn about it as well. So again, for you, the common material you need to realize is platinum, nickel, or copper. So make sure that you know that, and you can be tested in the exams in relation to these particular materials. RTD elements are fragile and are often housed in the protective probes. As you can see here, the probes and the protection, the outside kind of material protecting the RTD elements inside. Same is the case here. RTDs which have a higher accuracy and repeatability are slowly replacing thermocouples in industrial applications below 600 degrees Celsius. So another advantage of RTD is that for low, in order to get higher accuracy and repeatability means that below 600 degrees Celsius, the RTDs are pretty reliable in estimating the temperature, and they are replacing thermocouples, because thermocouples are, they lose their repeatability depending on their the time, how many times or the duration of their use, which basically deteriorates their repeatability. Then we will learn about it in the subsequent slides. Okay. So remember, the PRTs stands for platinum resistance thermometers, and SPRTs are standard SPRT stands for Standard Platinum Resistance Thermometer. So let's carry on, move on. The significant characteristic of metals used as resistive elements is the linear approximation of the resistance versus temperature relationship, and we will see the graphs in the subsequent slides. And that linear relationship exists between between 0 to 100 degrees Celsius. For these RTTs, the temperature coefficient of resistance is denoted by the symbol alpha and is given the unit ohm per ohm degree Celsius, and that's how the alpha is defined. The resistance at 100 degrees Celsius minus resistance at 0 degrees Celsius divided by, this is basically normalization to 100 degrees Celsius times R0. That's why the units of alpha are ohm, because on top there is only resistance, which we represent is as in ohms, and below we have temperature, which is in degrees Celsius, and R ohm, so that's why it's ohm over ohm degree Celsius. And as you can see here, R0 is the resistance of the sensor at 0 degrees Celsius, R100 is the resistance of the sensor at 100 degrees Celsius. So pure platinum's alpha is 3.9 milliohms per ohm degree Celsius in the 0 to 100 degree Celsius range, and is used in the construction of laboratory grade RTDs. Conversely, two widely recognized standards for industrial RTDs, and these are the standards. I don't expect you to remember these standards, kind of the numbers, and that's not meant, but anyhow, just as a learning point, that RTDs fall under, or for that case, any sensor fall under a certain standard, and specific and based on these standards, alpha for platinum for the RTDs, for alpha is 3.85 milliohms per ohm degree Celsius, and they are widely adopted. That's why we are discussing it. But in several different alpha values are you can find, and that's what they're saying, that the older values using platinum RTDs you will find is 3.916 milliohms per ohm degree Celsius, or 3.902 milliohms per ohm degree Celsius. Again, so what is alpha? Make sure that you understand that, and the units of alpha and the typical value of alpha for platinum RTDs. Okay, these different alpha values for platinum are achieved by, how they are achieved? By doping carefully introduced impurities which become embedded in the lattice structure of the platinum and result in a different resistance versus temperature curve, and hence an alpha value. Okay, so these kind of precisions are achieved by inducing impurities into the platinum metal or material in order to achieve the required resistance versus temperature curve. And we will see in the subsequent slide how it is we achieve it. Okay, but for now, since we are discussing RTDs, so what I did is I took this TMP 35, 36 or 37 low voltage temperature sensors from analog devices, because we are going to use TMP 36 in this in the lab, which we will do at the end of this lecture, and I will introduce you to that lab. And I wanted to discuss the information I found, very useful information. Whenever you are working with a device, sensor, chip, and any kind of electrical, electronic device you are working with, it's very highly recommended to look into the datasheets, because understanding that particular device features, that's the best source you can find from the manufacturer's datasheets. Since we are, as I said, since we will be using TMP 36 in the lab experiment, so that's why I took that information from the analog devices datasheet. Okay. So this is the functional block diagram of these RTDs, and as you can see here, this is the supply. The supply range can be 2.7 volts to 5.5 volts. Ground, the output voltage, because the material is embedded in there, so depending on the temperature, and you will get the different voltage at the output. It also has a shutdown signal, and by just looking into it, I'm pretty sure you know that what should be the signal you apply here in order to turn off the device. So that's what this device do. And you're right, the shutdown, this particular digital voltage level here has to be low, which is ground, in order to shut off or to save power, or numerous other reasons. Or one of the other reasons is to avoid longer use or constant use of the use of the material, to avoid deterioration of the material, and you can shut it down and only turn it on to make it high. And high goes, you can just pull it high to the supply. Or if you don't need that shutdown feature at all, you just simply just short it with the supply voltage, and the device will be on all the way. Okay. So, but some applications do require that you only want to turn the device on when you need to read the temperature, and that is the reason behind that, having that kind of a signal available for your sensor. Okay. So these are the different packages. In packaging, you can find this particular TMP35, 36, or 37. This is a SOT 23 package. This is an SOIC package, and this is a TO92 or T3 package. And depending on what you want to use, you can just pick your package selection, and you'll find all the signals in the respective package, as you can see here. Okay, so let's carry on. And this is what I was mentioning you. By just looking into the graph, the first thing you want to look at, that the graph is plotted between temperature on the x-axis and the output voltage in V at the y-axis. And but just looking into the lines before going into the details, you know that these are linear lines. Okay? So they have linear relationship. These ICs have linear relationships between temperature and the output voltage. The line A is for TMP35, the line B is for TMP36, which we will use in our experiment, and the line C is the TMP37, and the supply voltage, of course, of supply voltage of 3 volts. Okay. So as you can see, the data sheet giving us an immense important information related to the RTD sensor. So let's carry on. And again, from within the data sheet, so this is kind of a reference circuit, that how you can use this IC if you just simply want a temperature in degrees Celsius. You can just simply use a decoupling capacitor, 0.1 microfarad. We already talked about it. Most of the ICs use the decoupling capacitor to avoid any noise from the supply or from the environment, to improve the reliability of the functioning of that one particular IC. And you can go ahead and read it. This is exactly the same which I told you in the previous slide. And this particular temperature circuit is, if you want the temperature, the output voltage as in Fahrenheit. You want the temperature as in Fahrenheit thermometer. So it's basically simply using scaling resistors in order to get the voltage, which basically corresponds not only the resistors, but also is using a Zener diode as well in order to get the voltage, which will give you the temperature in Fahrenheit. Okay, and these are the values of the resistors also given to you. So again, it's a very important learning point, is that by just reading the data sheet of a certain chip will give you immense time-saving information, quality information, without you to go ahead and just basically try to relearn things. you can save a lot of time by consulting the data sheet, taking the reference circuit, testing it out, and using it in your particular design. Okay, so let's carry on. So let's talk about calibration. So there are two, kind of calibration schemes mentioned here. One is fixed point calibration, the other is comparison calibration. So I think since it's a very important topic, so let's read it quickly and try to understand it. To characterize the resistance versus temperature relationship of any RTD over a temperature range that represents the planned range of use, calibration must be performed at a temperature other than 0 to 100 degrees Celsius. This is necessary to meet calibration requirements. Although RTDs are considered to be linear in operation, it must be proven that they are accurate with regards to the temperature with which they will actually be used. And two common calibration methods are fixed point, and so let's learn about fixed point. Is used for the highest accuracy. Okay, calibration by National Meteorology Laboratories. It uses a triple point, freezing point, or melting point of pure substances such as water, zinc, tin, argon to generate a known and repeatable temperature. So very important terms: known and repeatability. These cells allow the user to reproduce actual condition of this is a standard ITS 90 temperature scale. Fixed point calibrations provide extreme accurate calibration within. So the important thing here is within plus minus 0.001 degrees Celsius. A common fixed point calibration method for industrial grade probes is the ice bath, which is not that accurate. Its accuracy is about 0.005 degrees Celsius compared to 0.001 mentioned in this ITS 90. But that accuracy is kind of good for the industrial grade probes. Okay. So the comparison calibration is commonly used with secondary standard platinum resistance thermometers and industrial RTDs. The thermometers being calibrated are compared to calibrated thermometers by means of a bath whose temperature is uniformly stable. Unlike fixed point calibration, comparisons can be made at any temperature between minus 100 degrees Celsius to 500 degrees Celsius. This is the equivalent in Fahrenheit. This method might be more cost effective since several sensors can be calibrated simultaneously with automated equipment. These electrically heated and well stirred baths use silicon oils and molten salt as the medium for the various calibration temperatures. Okay, so in simple words, in relating to this particular course, what I emphasize again, need the highlight point, the two type of calibration: fixed point and comparison calibration. And for the fixed point, the industrial grade calibration, kind of accuracy is 0.005 degrees Celsius, but the highest accurate one is 0.01 degrees Celsius. So you need to know these, kind of accuracy ranges. Be very sure on it. Be very clear on it. And again, for the comparison calibrations, it is between minus 100 degrees Celsius to 500 degrees Celsius. Okay, so enough a kind of information, or the basic information required in relation to that. What is calibration, and different type of calibrations, and the accuracy within fixed point calibration, and the range of temperature for the comparison calibration. Okay, so let's carry on. So this is a very important slide, I'll say. So it's basically comparing RTDs with thermocouples. Thermocouple is another type of temperature sensor. So why we are comparing it? Because the two most common ways to measure temperatures is basically either RTDs or thermocouples, and which one to use is based on these parameters. And the first is obvious, the temperature, the response time, the size, and the accuracy. So if the process temperatures are, if the temperature need to be measured is between minus 200 to 500 degrees Celsius, an industrial RTD is preferred option, and thermocouples are preferred because they cover a very wide range, minus 180 to 2320 degrees Celsius. So the temperature about 500 degrees Celsius, we consider using thermocouples, and they are contact temperature measurement devices, and that's why they are very accurate. So if their response time is also very is very good, and if the process requires a very fast response to the temperature changes, then a thermocouple is the best choice. Time response is measured by immersing the sensor in water moving at 1 meter per second with a 63.2% step change. Regarding the size, the standard RTT sheath is 3.175 to 6.35 millimeter in diameter. Sheath diameter for thermocouples can be less than 1.6 millimeters. So basically, as you can see here, the thermocouples, very advantageous when it comes to, and when we're talking about the size, the response time, or the higher temperature ranges. When it comes to accuracy, RTDs are more accurate because, okay, let's learn about it. If a tolerance of 2 degrees Celsius is acceptable, the highest level of repeatability is not required, a thermocouple will serve. Again, tolerance of 2 degrees Celsius is acceptable and repeatability is not required, then thermocouple will serve. RTDs are capable of higher accuracy and can maintain stability for many years, while thermocouples can drift within the first few hours of use, because we are talking, see the temperature ranges, depending on what temperature range you're talking about, they drift, and that drift means less accurate compared to RTDs. Okay, so let's carry on. And this is how the RTDs are constructed, and here's your resistive element. This arrow means varying with respect to temperature, and these are the connection leads. Okay, and the connection leads are coming out. This is your sheath, as you can see here, enclosed in a sheath, and this is your insulator around your connection leads, which basically comes out and which you use it in your circuitry. So the two most common, I'll say not two, three most common configuration is the 2-wire, 3-wire, and a 4-wire. In the 2-wire, as you can see, this is your RTD element, changing the resistance with respect to temperature. This bridge serves in order for you to detect the voltage variations between these 2 points in order to estimate the temperature measured or detected by the sensor. The 3-wire, why we use the 3-wire configuration? The 3-wire configuration is to minimize the effect of lead resistances, and again these are the leads. To minimize the effect, that's why we use the 3-wire configuration, and again the measurement point is the same. Okay, and this is where we supply the voltage in order to the power of the circuit in order to have the current flowing and be able to detect respective voltage variations because of the change in resistance and obviously current flowing through the RTD. And this is the 4-wire configuration. Again, the 4-wire configuration increases the accuracy of the measurement of resistance. 4 terminals eliminates voltage drop in the measuring lead as a contribution to error. So the reason behind why we use 3-wire or 4-wire configurations. Okay. And this is the picture of the the RTD sensors, and this is is your sensor attached with the mechanical setup in order for you to bring it to your respective whatever electrical electronic instrumentation device, so that you can measure your temperature. So there are three type of PT100 sensors I'm showing you here, and different size and different kind of look and feel. Okay. And this is the temperature dependent resistance for various popular resistance thermometers or RTDs. And this is the temperature, this is the respective model number of the RTD, and their resistance is in ohms, as you can see here, at different temperatures. So minus 50 is 79.9 for this RTD sensor, 80.31 for this PT100, PT1000, 803, and so on and so forth. And you see the NTC type 103, how big is the value of that resistance. Depending on what is your application, what you want to do, you can basically, very important for you to consult a temperature chart like this one. Okay? So I just brought it here for you to get kind of a clarity on very important feature relating to RTD sensors. So now let's move on to thermistors. So what is a thermistor? As I told you right in the beginning, it's a combination of two words, therm for temperature or thermometer, and resistor, combining these two together is the word thermistor. A thermistor is a semiconductor type of a resistor whose resistance is strongly dependent on temperature. More so that in standard resistors, the word thermistor is a combination of thermal and resistor. The first NTC thermistor was discovered in 1833 by Michael Faraday, who reported on the semiconducting behavior of the silver sulfide. Faraday noticed that the resistance of the silver sulfide decreased dramatically as temperature increased. So any thermistor or a temperature sensor where the resistance decreases with respect to increasing temperature, that called to be as a negative temperature coefficient, or NTC. Okay, is the word we use it. This was also the first documented observation of the semiconducting material. So negative temperature coefficient, NTC, as I mentioned here, is kind of a temperature sensor where by increasing temperature, the resistance decreases. Thermistors have less resistance at high temperatures, while positive temperature coefficients are alternate or reverse of NTC, have more resistance at high temperatures. NTC thermistors are widely used as inrush current, and if you're not sure about this inrush current, whenever you turn on any electronic device, the current utilized by that particular device is the inrush current. Okay, any motor, electronic, battery operated, whatever equipment, when you turn it on, it uses what we call it as the inrush current. Okay, so more onto it, if you're not clear, ask during Q&A sessions, okay, to be further clear on it. But in simple terms, whenever you turn on an electronic device, the current which rushes into that particular circuit is known as the inrush current, and that stabilizes to normality within few, depending on what type of circuit is it, within no time, that inrush current dissipates. So the NTC thermistors are widely used as inrush current limiters and temperature sensors, while PTC, positive temperature coefficient thermistors, are used as self-resetting overcurrent protectors and self-regulating heat elements. All pretty, I think, self-explanatory terms. An operational temperature range of a thermistor is depending on the probe type and is typically between minus 100 to 300 degrees Celsius. Make sure that you know that. And thermistors are typically built by using metal oxide. You use the material depends on which type of sensing behavior is required, NTC or PTC. And here I'm showing you the picture of a thermistor, which is an NTC thermistor. It's a passive element. It means you have to provide power so that the current will flow in order for this sensor to work. And electrical resistance, and here is its electronic symbol. Okay, so let's carry on. And the basic operation is, that's what the assuming a first order approximation, the relation between resistance and temperature for a thermistor is given like this. Delta R is the change in resistance is equal to K and the change in temperature, and the K is the first order temperature coefficient of resistance. Depending on the type of the thermistor in question, K may be either positive or negative. If K is positive, the resistance increases with increased temperature, and the device is called, again, the same thing as we talk about PTC and NTC. Instead of temperature coefficient K, sometimes the temperature coefficient of resistance, which we call it as alpha T, is used, and that alpha T is defined as 1 over RT, the change in resistance with respect to temperature, and this is rate of change of resistance with respect to temperature. And so anyhow, it's beyond this course, but for you to really for you to be, I'm sorry for that, for you to be really kind of clear that you know that this is the basic operation, and sometimes the alpha T term is also can be utilized relating to thermistors. Okay, and make sure that you understand these terms and what is K, and it is depend on whether it's positive or negative. So let's carry on. So here what I did, whenever you are looking for an electronic device, as I recommended you look into DigiKey. It's a very well-known kind of electronic component distributor. And what I did there, I simply just put the word thermistor, and here what you can see here, it's showing you here the NTC thermistors, you know, roughly around 11,000 they have items available, and PTC thermistors, you know, roughly around 970 items. And as you can see here, they just look like, you know, an SMD resistors or capacitors, okay, like tiny devices, and you can see their prices and availability as well. So here is the typical applications of using a thermistor for temperature, kind of detection. In this application, this is the hard disk kind of a magnetic head, and this is where the thermistor is used, which is of NTC type. And because this is like a voltage divider, and the temperature changes this resistance, so the voltage here, changes, and there is an A to B or analog to digital converter, and the digital voltage goes to the CPU, and there is an interface, and depending on, what you want to do, maybe, you control the speed of the head or whatever application you need to do in order to have a safe operation or read and write operation on the magnetic hard drive. GMR is, the head is basically called the hard drive heads for the read and write. And here another application is for the contrast level control of the LCD. Again, here is your thermistor, and that the variation goes to the LCD in order to control the contrast of it, depending on what you want to do relating to at what temperature to have a safe operation of that particular LCD. And here is PMIC is basically for the power management, and here is the thermistor used there for respective application. Okay. So Further discussing applications, for temperature monitoring is HVAC and thermostats, industrial controls and appliances. Pretty common. Thermal compensation for display backlights, building automations, motor control, for chargers, and there are some of the basic, typical application circuits which we discussed in the last slide in here, as you can see here as well, just like voltage dividers. Take advantage of the benefits of our NTC thermistors, such as no extra linearization circuitry. So again, using NTC thermistors, we don't require any extra linearization circuitry. Minimum calibration required, less resistance tolerance variations, larger sensitivity at high temperatures, and simplified conversion methods to save time and memory in the processor. So what we are learning that prefer, if you don't need specifically a PTC thermistor, go for an NTC thermistor provided that falls within your temperature range. The TMP64 is currently available in 0402. So this is the size of the SMD. Footprint compatible, excellent sound package, and 0603 footprint compatible SOAT 5x3 package. Okay, so that's what it is, and here's the temperature to resistance kind of a curve. And as you can see, it's not that linear, but as you can see here, that's why you need to. You can assume this to be almost linear, but I see a bit curve in here, so it means it does require a bit of a software calibration, or maybe a calibration in the circuitry in order to achieve the required accuracy in your design. Okay, and here you can see the respective equations for the circuit. Very simple and straightforward. So let's carry on. So now let's discuss the last type of temperature sensor, and that's called a thermocouple. And a thermocouple, also known as thermoelectrical thermometer, is an electrical device consisting of two dissimilar electrical conductors. One type of electrical conductor, the second type of electrical conductor, forming an electrical junction. Okay, and that electrical junction is basically the reason is basically which helps us detect temperature with the highest accuracy. So the K-type thermocouple, which is a chromal aluminum thermocouple, in the standard thermocouple measurement configuration, the measured voltage V can be used to calculate the temperature, the T sense here, and provided that the reference temperature here is known. Okay, so what's so as you can see here, this is one type of a kind of a metal. That's another type of metal. That's why you have a junction. The temperature is sensed here, and because of the difference in the type of materials, okay, you detect, you have a reference temperature here, and ultimately because of that different materials, you detect a difference in voltage here, which basically depicts what temperature is sensed on this side of the junction. So as you can see here, this is a thermocouple connected to a multimeter displaying room temperature. So here's what it is, where the junction lies, and the wires are coming in. So this particular multimeter has that capability to read thermocouple voltages, and internal they have an ADC, and that's how you can read that it's 19 degree Celsius. Most commonly it's going to be in Celsius what you are reading here. So it's basically a thermocouple is basically two dissimilar or two different electrical conductors forming an electrical junction, and because of what you're able to read voltage variations and be able to properly or accurately measure the temperature at the sensing point. Okay. And here's another very good picture, and in this if you see here the reference junction block inside a fluke CNX T3000 temperature meter. Two white wires connect to a thermistor. White wires connect to a thermistor embedded in white thermal compound to measure the reference junctions and temperature. So again, that's a good example, that how these are used in different again, but this is not thermo. This is thermistor. This is not a thermocouple, so this is for the thermistor. Okay. But as you can see, miniaturization of electronic devices is is pretty significant and always evolving. Okay. So let's move on. So a thermocouple's brief history. In 1821, the German physicist Thomas Johann Seebeck discovered that a magnetic needle held near a circuit made up of two dissimilar metals got deflected when one of the dissimilar metal junction was heated. Okay, so the observation by a German physicist Thomas Johann in 1821. At the time, Seebeck referred to this consequence or the observation as thermomagnetism, but later on, the magnetic field he observed was later shown to be due to thermoelectric current. In practical use, the voltage generated at a single junction of the two different type of wires is what is of interest, as this can be used to measure temperature at very high and low temperatures. The magnitude of the voltage depends on the type of wires being used. Generally, the voltage is in microvolt range, and care must be taken to obtain an usable measurement. Although very little current flows, power can be generated by a single thermocouple junction. Power generation using multiple thermocouples, as in a thermopile, is common. So again, just a brief history that that particular dissimilar metals resulting in a variation of current based on temperature was observed by a German physicist in 1821, and good to know the history behind that. Initially it was thought as a thermomagnetism kind of a behavior, but repeated experiments confirmed that it's not thermomagnetism, but it's because of thermoelectric current. Let's carry on. And here are some very important graphs to refer to in order to understand thermocouples characteristics of different materials. So as you can see here, there are the different materials. The temperature is on the x-axis, voltage with respect to T, AT, and millivolts on the y-axis. There are type E, J, M, K, and different type of materials. So let's understand that, what type of materials these are. The characteristics function of the thermocouples that reach intermediate temperatures as covered by the nickel alloy. So these are all nickel alloy thermocouples of type E, J, K, M, and T, also known Also shown are the noble metal alloy type E, uh, alloy type P. So where it's the noble metal alloy type P, yeah, right here, okay. And the pure noble metal combinations gold platinum and platinum palladium. So these are, in simple words, these are all different type of materials, metals. And as you can see here, some, this is pretty linear. As you can see, temperature with respect to, the voltage you will get. And this is linear. In simple words, you need to see that which type of a material is going to give you the required objective or function in your desired circuitry or needs. Okay, but as you can see here, this graph goes from 0 to 1500 degree C, and this goes from 0 to 2500 degree C. Very important information in relation to thermocouple sensing characteristics. And here, this is minus 270 to 0 degrees Celsius, and this is for this is type N. In this one, the only linear one is this this black chromel AUFE 0.07. That's the most linear material you can find in this particular graph, and it will be very useful if you are working in this particular temperature range. Okay, so let's carry on. So now here is the experiment we are going to do for this particular lecture session, and in this I'm going to demo you this work as well, but let's understand what we are doing here. So in this one, this is our TMP 36. We're using this. We are using Tinkercad to do this circuit, but we will also do it using the breadboard, as well. I have provided you all the connections, all the circuitry, all the software. So technically, you simply have to understand that what you are doing, and in order to get this work done. So here we have three, I'll say, sensors. So one is this. This is the soil moisture sensor. It's from SparkFun. If you just click here, you will go to the detail. But in this Tinkercad, this is available. It's very handy. And in this, you can see here that it's connected with the ground, an A0, A1 line, and A0 line is basically just there to use it, this A0 as a digital kind of a line. And you will learn, as you can see here, A0 is an output, so it means this is just as a digital line. Then A1 is the input line where the analog voltages are coming in. So this is the soil moisture sensor. It will detect the moisture in the soil. This is a TMP36 sensor, which basically is kind of a thermistor, which we will use to measure the temperature, and it's connected, as you can see here. So this is its analog A2 line. There it is coming in, and this is simply the power and the ground connections. Okay. This the third type of I'm also going to call it as a sensor, because this is just emulating any other type of a temperature sensor, because this is a pot. It varies the resistance, and the change in resistance basically causes the change in voltages, That's why it's just basically working as an emulator. And this is the line, the analog, which goes to A3 to be the analog voltages. So again, so three type of sensors: soil moisture sensor, the thermistor, and the pot, which is basically an emulator. And these LEDs is basically for the soil moisture sensor. This LED is for the pot, and this LED is for the TMP 36. And this voltmeter I have connected here just to show you that I am basically reading the voltages as I change the temperature over here. So what I'm going to do, I'm just going to demo you this, that how it works before going further into this detail into the code. So here is okay, I think I have to exit here, and I'm going to go in here. Here we go. So this is the Tinkercad. This is the project. So let me demo you that. So I'm starting the simulation. And here you go. As you can see here, it's simulation has started. I'm going to show you my code window as well, and I'm just going to move them here. And the reason of showing you this because there is, see there, monitor here. You can see that I am printing the values. Okay, so you see here, as I change the pod to the minimum, okay, so the pod reading is 0. When I move the pod high enough, you see this LED goes on. See this? And you can see the values here as well changing. And if I go back, and if I bring the pod back, and the LED goes off. Okay. So see this TMP 36. So see, I change. Technically, when you will do this on the breadboard, you can use any blower or any way to heat up this TMP 30 TMP or thermistor, if you have it. If not, just emulating is good enough for now. But the minimum I required for the lab is that you use a pod, because it's very simple. You can find it, you can use it, you can use different resistors in order to show your work. Okay, so this is the minimum as a requirement for the lab work when you're doing the prototyping. If you can find these two, that's good, which I really doubt, since we are almost in the last lab. So if not, don't worry about it. But on Tinkercad, you have to have same kind of a functionality in order to get proper grades in this particular lab. So you see here, so temperature is at the minimum, and you see the voltage, the voltmeter, so I'm increasing it. See, the voltage is increasing, and as soon as I cross the threshold point, and the LED goes red. So if I go back, it just turns off. Okay. So now I'm going to do the soil moisture sensor. So you see here, and you'll see all these LEDs, and I'm going to move the sensor for the series. Here we go, and here we go. So that's our soil moisture sensor. So it all works. So the reason of showing you all that because this is expected of you to do it, and this will give you a quick learning online, and also when you do the prototyping as well. Okay, so let's go back to the lecture, and I'm going to explain you that the code. So let me from the current slide. So again, as you can see here, so I have defined these variables. Initialize them to be 0. This is a string variable. I just make it as a kind of a null string in the beginning, This is just for debugging purposes. The setup, as we all know, only just this function runs in the beginning. I'm setting all the pin modes. A0 as an output. The rest are A1, 2, 3. They're all input analog channels. And I'm making my serial port baud rate as 9600 bits per second, and these are the output pins for all these LEDs, and that's, you can just simply go and make sure that that these are the pins that we are using. Into the next one, I'm just putting that setup again here as well, just for completeness. Then we come into this loop function, and this loop, as we all know, runs forever. And what I'm doing here, apply power to the soil moisture sensor, and that's why we basically just make A0 line high so that it starts functioning, and this delay just so that we can kind of have adequate response, be able to see that what's going on with our design. And here we read the A1 channel from and we read the moisture value. And this is just for debugging, and just making this, what is the reading? This is what I'm converting the red digital value into string, and I print that string into that debug window, which I just showed you. And as you can see here, and now I'm turning off the sensor to reduce the metal corrosion over time. And as you can see here I made it on to read the value. Then I made it off. Then I print at what value I'm getting. Then I write, to the respective as low, to the respective soil measuring LEDs, make them as default as low. And if the moisture is in a certain range, as you can see, very simply if and else statements, I make the respective LED go high. That's all what it's doing related to measuring the soil moisture. And this is where I'm using reading the TMP36 analog channel. I'm reading A2, and again putting into this variable, and this is my debug string. I'm printing what the value I'm getting, and here is just a simple if-else statement. If the value red is greater than 200, then make the LED high, else make the LED low. Again a delay, and the last one is I'm reading the port channel which is connected on analog input channel 3, and if the port reading is, again it's a debug string, and if the port value red is greater than 510, I will turn on the LED, else I will leave the LED low. So this is, as you can see here, that everything is given to you. It's expected that you will do the online using Tinkercad 100% as I showed you, and be able to see your work, and in order to get that 40% of it. And regarding the breadboarding, the least which is required, that you demo this work using a pot, a potentiometer. And even if you don't have a pot, you just use different resistors in order to show that functionality and be able to achieve that 40%. But the rest of the 20% is related to your lab report. Okay. So the last one is here are the references. So please, if you still have any questions, keep it for your Q&A session, and we will discuss in order to further clarify any questions you have in your mind. Okay. Thank you very much, and have a nice day. Take care.